Hi, this is Steve Conklin, AI4QR, and this is the second video that I've done talking about XNEC2C and how to model antennas with that. Now, we're going to talk today a little bit about the file formats, the input parameters that go into the antenna model, and information about this. The easiest way to find it is to go to ai4qr.com, which is my web page. And from there, I'm going to link the videos and any support information, which will be on my blog, and I can update that as needed. Now, if you haven't already fetched the antenna models that I use as examples, you'll need to pull those from the Git repository. I keep them on GitHub, and we do that with this git clone command that's on the screen now. And it's not a very big repository. It'll pull very quickly, and there we are. Now, if you have this from last time, I've changed a few files in it. You'll need to update that and get the very latest. And you do that by, once you're in the directory with the antenna modeling files, you git pull origin master, and I'm already up to date, but if you weren't at this point, it would have updated it for you. Now, if you look in this directory, two things of note here. One is this NEC2PRT3 PDF file, which is the sort of user manual for these input data files. Some of the things in that's very old and actually documents the card format file from when it was an old Fortran card deck application. Some are not supported by XNEC2C, but the reference cards are all well documented on that. And the other thing is that I've written a script in dump NEC that dumps these cards, these input files out in a human readable form so that you can see what the various card fields mean, because they change card to card. We'll talk about that in a second. Now I'm going to open the example I'm going to use is this vertical sample.nec, and you can open that in any text editor. And this is the entire file. It consists of a comment section, which is the first two lines, comment begin and comment end. You can have as many comment lines as you want, but they all have to be at the beginning of the file. What we're going to talk about today is the geometry of the antenna, how the wires are defined. We have one wire in this antenna, and it's with a geometry wire card and then an end card. And then we're going to talk about the ground plane definition, which is down here. And that's about all we're going to have time for today. Now, the first card in the geometry section defines a wire. This vertical antenna is one single wire. The first field in this is a wire number, a tag that is referenced by other cards, other lines in this file. The second is the number of segments in this wire. The modeling software divides a wire up into segments to run the analysis on. The more segments you have, typically the more accurate the simulation is, but within limits. The lower bound is about 1/10 of a wavelength per segment. You don't want to have your segments longer than that. This is a quarter wave vertical antenna, and we're dividing it into 32 segments, which is 128 segments per wavelength, so each one is smaller than 1/100th of a wavelength, so we're well under the limit here. And complex antennas sometimes need more smaller segments. The next field after the number of segments, the next three fields are the beginning of the wire in X, Y, and Z coordinates, and it begins at the origin 0, 0, 0. The next three fields are the end of the wire, which is X is 0, Y is 0, and Z is 7.5 meters. So this is a 7.5 meter tall wire. The last field in this is the radius of the wire. So This is 25 millimeters radius. 25 millimeters is about an inch, so this is about a 2-inch mast, quarter wavelength antenna. The geometry definition for the antenna ends with a GE card, and the only field that's significant on this is this 1 in the first field after the card name, which tells us that there is a ground plane in use for this model. If you define more than one wire, we'll get into this in a later lesson, and the endpoints for wires are at the same coordinates, then they're considered to be connected together. So all you have to do to connect them is make sure that the ends are at the same point. Now, the ground definition down here is the first field is a 0, and that tells us that we're using something called a finite ground reflection coefficient approximation. There are a couple of different, 3 different models that you might want to use. One is this finite ground model, one is a perfect ground model, and the other is yet another model. This is good enough for most of what you want to do when you're modeling antennas. These models are not terribly accurate in real life due to terrain effects on the propagation pattern and a lot of other things, but they're useful for investigating different antennas and learning more about it. There's a really good chapter in the ARRL antenna book, and I'll link to that in the blog post about this. It tells you why these models aren't perfect and when they break down and which model. There's another modeling program that unfortunately is Windows only that can do some things this can't with terrain modeling. And there's a very good chapter in that antenna book that describes exactly what I'm going over now, which is the data input for the modeling software, and it includes a great deal of depth in how to define traps and impedances in the antenna and other things like that. So back to the ground plane definition. 0 is the finite ground model. The second field is the number of radial wires that we have radiating out along the ground at the base of the antenna, and this is to improve the ground plane and the propagation and the radiation resistance of the antenna. The next 2 fields don't mean anything for this model. The floating point field, these 2 define the parameters of the ground itself. The first one is the relative dielectric constant of the ground, and the second one is the conductivity of the ground in moles per meter. Now, you can get all worried about getting these exactly right for your location, but there are maps that show what the average is in different parts of the United States or the world, wherever you happen to be, and you can use those. It varies quite a bit depending on whether you're on dry, sandy soil or over marshland or over water, for example, on a coastal installation. The next field is the length of the radius of the radial field under the antenna. So those 32 wires are each 10 meters long in this case. And then this last field for this model is the radius of the ground radials, which is 5 millimeters, which means the diameter of those wires is 10 millimeters, which is pretty thick wires, but that's what's used for this model. So we've defined the antenna geometry, we told it we're using a ground plane, and we defined the ground plane. Now we're going to go and fire up the fire up XNEC2C. We'll open that file. And we can see that vertical wire. That red segment is the excitation. We didn't talk about that, but if you look at the excitation card, it's the EX card, you'll see that we're exciting wire number 1, or tag number 1, which is the only wire there, and segment number 1, which is the first segment in that wire. Now if we view the radiation pattern, this is a very typical pattern for a ground plane with a quarter wave dipole above it. And it's omnidirectional, equal in all compass directions, and has an elevated pattern because of the reflections of the waves off of the ground plane. So that showed you how to define a very simple vertical antenna. Next one we'll probably do a dipole or something with more than one wire and talk about how to model that. But this has been a good, I'm going to try to keep these to 10 minutes. This is a good 10-minute lesson. If you're really deeply interested in this, I highly recommend the ARRL antenna book. And you can also read through that NEC2PRT3 PDF file and get an idea for the different cards in the deck. And then again, you can use the dump. If you change the file, you can use that dump NEC script that I wrote to get an idea of whether it's doing what you think you changed or not. So until the next lesson, this is AI4QR. You can find more on my website, and I'll put up a blog post with a link to the antenna book and some other things. And I hope you enjoyed this. Send me email and feedback, and I'll try to get these out a little more often. Thanks.